Welcome, Regents students. Today's topic is refraction, the phenomenon of refraction, and the equation of Snell's law, which quantifies how much refraction happens for a given substance. First of all, what is refraction? Well, at this point, you should have watched the short video, I think it was like 40 seconds, that I included in our classroom stream that shows refraction happening. If we were in class, as I've said many times, I would get out a laser and a fish tank and I would shine the laser and we'd see the light bend. But unfortunately, since we're not in school, you have to watch a video. But the video did a nice job showing the laser light come into the tank, and then you should have seen it bend at an arc. If you missed that, then go back and rewatch the video to see that. So that's refraction. That's what it is. It's the bending of a light ray when the ray encounters a medium. So, or a boundary, a medium change. So there are a couple examples. So the first example, what I have is I have index 1 less than index 2. So for example, maybe the light starts in air, index 1, and then it goes into glass, which, you know, one of the glasses is about an index of 1.7 rounded to two significant figures. So we're going from a low index to a high index. And what we saw in the video, the light bent like this when it went into the water in the tank. It did not go straight, so that dotted line shows the straight line path of light. But some of it bent like that. We say that the light bent towards the normal. Okay, so it's. I just want to point out that by saying the light bends toward the normal, doesn't mean it's going towards the normal. It's still moving away from the normal, right? So here's the normal, and as it's moving, it's going further and further away. What I'm saying is that if the light were like a wire, you take it and you bend it like this, and that's now how it travels. So it gets sort of distorted a little bit in the direction of the normal. This is what we call the refracted ray. It's at a different angle, a smaller angle than in material 1. But another thing that you need to know is that when light refracts, some percentage of it always reflects off the surface. What percentage is more complicated than what's in the course? Maybe we have 50-50% of the light. Maybe 60% goes in, 40% reflects. It varies depending on the conditions. But you do need to know that the light comes in, and when some of it reflects at the same angle according to the law of reflection, some of it refracts going in. Okay? And theta 1 is greater than theta 2, right? So that's the bending. The other possibility is that we start in the higher index instead of starting in the lower index. So we start in maybe like glass first, and then the light is going incident onto air. What happens then is, rather than the light traveling in a straight line, it bends, like if this were a wire, I'd bend it away, and then it travels even further away from the normal. So that's the bending action. So that means that theta 1 is now less than theta 2 because this increased. And again, some of the light is reflected perfectly according to the law of reflection. So that is what refraction is, that bending of light. Take a minute, pause the video, and copy this in your notes to the best of your ability. Okay, moving on. What we want to do is now find out how much this bending occurs. A formula. That's where Snell's law comes in. Okay, so here's Snell's law. And if you look at this formula, it kind of captures the information over here. In other words, let's suppose we have a certain n over here, 1.0, and then maybe this is like 60 degrees. So we calculate as we get some number over here. We go into a higher index. In order for the equality to be preserved, if this is bigger, this has to compensate by getting smaller, which we saw over here. But if, on the other hand, we go into a higher index, so a lower index. Before, this was bigger, made that smaller. So now let's suppose we go like this, from 1.7 to 1.0 over here. So this all comes out to be some number. If we plug in theta 1 and n1, we get some number over here. If this gets smaller, in order for this to be preserved, this has to compensate by getting bigger, bending away from the normal. So the information that we learned in this part of the notes is within this formula. So take a minute, jot that formula down. The last thing, or not the last thing, next thing we're going to do is we are going to do an example calculation here. So we've got a piece of flint glass, a block of glass in water, surrounded by water. The light's coming in like this. So I covered this up because I drew the light ray in the material. I want you to think about water. First of all, I'll mention this. It's got an index of 1.33 and this is 1.66. So we're going from 1.3 to 1.7. We're going to a higher index. Does the light bend towards the normal or away from the normal? Okay, so pause the video, think about it, and decide. All right, well, you should have said towards the normal. Okay, so there's a sketch of the light bending towards, right? So this is the straight line path. It bends like that, smaller theta 2. So here's how we do the calculation. We start with Snell's Law. We write it out, as always, in the Regents. We go to the reference table. We got to look up water and flint glass, the indices of refraction. So I go to page 2, and right here I see water, which is right here. Oops, off the screen. Move this up a little. Water, 1.33. So that goes right here. Okay. And then in substance 2, that's the flint glass. So I look up glass, comma, flint, 1.66. So that's what goes in right there. So I got my two indices, water, glass. Okay. The angles. Okay, so notice I gave you this 20 degrees. This is a common thing in Regents. Remember how I said throughout the year that kind of in a cynical manner that the Regents likes to trick people to make more people get questions wrong? And I don't know if they really do that, but it seems that way. Very often they'll give you this angle like this to the surface, 20 degrees, to make you plug in 20 and get the wrong answer. But that's not how we measure angles in optics. Remember in video lesson 1, when we were learning the law of reflection, the angle's always to the normal, right here. And so it's 90 minus 20, or 70 degrees. The other picky point is, this is the unit. If you don't write degrees, remember how I said you get a 1 out of 2 on this problem? So you get all this, you get the right answer. You left off that little degree mark. 1 out of 2, 50% F on this problem. So again, Regents very harsh with their units. 70 degrees, you got to put that in there. And again, these don't have units index. So I multiply these out. You have to be in degree mode on your calculator, not radian. So if you have it in radian for math, take it out for physics, put it in degree mode, multiply these, and then divide by 1.66, you get 0.75. And then what you do to get, so sine theta equals 0.75, the way to solve this is you have to do the inverse sine. So on your calculator, you'll see second sine gives you sine to the minus 1. Inverse sine of 0.75 gives you the angle of 48.8 degrees. All right, so take a minute, pause the video, jot down this example into your notes. Okay, so in class there would be more demonstrations, but again, as I've said so many times, you know, we can't do that. The next thing that I want to talk about is some consequences of Snell's law in refraction. So also I should have mentioned, we have reflection, refraction, and remember in waves we learned diffraction, when light spreads through an opening. So 3 words that sound very similar. You're going to have to keep those separate for the Regents. Reflection, well, people kind of know what that is. That's kind of, you know, use that. But diffraction is when a wave spreads through an opening. Refraction is when it bends at a boundary. All right, so here, I would have had a prism and shine white light, and we would have seen a rainbow come out of the prism. Okay, so the fancy word for that is called dispersion. And the dispersion is the separating of white light into colors through diffraction. So white light, as you probably know, is a mixture of all the colors of the rainbow. Put them all together and somehow it looks like there's no color there, it's white. So this white light comes in, I have a piece of glass that's like a triangular shape like that. It hits the glass. Now look at this ray, right here. Hits, and here's the normal. Because we go from low index air to high index, like maybe 1.6 or 1.5, whatever kind of glass it is, we bend, instead of going straight, we bend a little toward the normal. Now that light goes through the glass, it hits air again, goes back to air, and here's the normal. And instead of going straight, it bends away from the normal because we're going to a lower index. So it bends twice. Once right here, it bends, and then when it hits here, it bends again. And that happens for all the light. Light here also bends. But when we do that, we see that the rainbow emerges. We have red, orange, yellow, green, blue, and violet. Okay? So why did that happen? What you would actually see, well, let's take a look first of all at our reference table. There was a frequency up here, 5.09 times 10 to the 14th. The reason why is that these indices were calculated or determined experimentally for this kind of light, which if you look up here is yellow light. It's one of the lights that comes out of the sodium atoms when they're excited. But the reality is the index of refraction changes with wavelength. If you take a different color out of this spectrum of light, the index of refraction will not be 1.52. It might be 1.51 or 1.53 for crown glass. It turns out that red light has a slightly smaller index of refraction in glass. So it bends less and ends up here. Whereas violet light has more or a higher index of refraction. It bends more. So rather than bending and ending up in the same place as the red, it bends more over here and ends up over here. So that's why rainbows are formed. Now in the case of glass, you could make it with glass, but also they're made obviously in the sky with water droplets. So you got 1.33 surrounded by air 1.0, and it hits the droplets and spreads out. So that's because the violet bends more than the red. So that's all you need to know, is just the concept. You don't need to know these numbers, you just need to know that red light bends a little bit less and violet a little bit more, and that takes white light and spreads it out into the rainbow, and the word for that is dispersion. Okay, another demonstration I would show you. Today I would show you a lot of demonstrations if we were at school. There's only one that I think is most likely to be on the Regents, so rather than go through and make these notes hours long with all kinds of different things that can happen with refraction, I'll show you one last thing, and that's how refraction creates illusions in terms of depth. Okay, so and by the way, there's a video that I'll also include in the stream that you could watch if you want. There's a man who puts a coin in a bowl and he makes it disappear first and then reappear because of refraction. So it's kind of nice, just a couple minutes if you want to look at it. But here's what happens. So let's suppose you're hunting next to a body of water, maybe a pool that has fish in it or something like that. And you're hunting with a spear instead of a fishing line. And what you do is you take the spear and you throw it directly at the fish or where you see the fish. The problem is if you do this, you will miss because of refraction. Let's suppose this is the actual location of the fish right here. The light that comes to your eyes starts off at the fish. That's how you see it. Light has to come off the fish and go into your eyes. When it comes here and hits the boundary, though, it doesn't continue straight because of the refraction. We've got water 1.33, air 1.0. Light bends when it goes to a lower index away from the normal. So the light off the fish goes like this and makes a slight turn and goes to the hunter's eyes. Now the hunter is going to say, well, the fish, I'm going to throw directly at where the image is. So the hunter throws directly in the opposite direction the light came. But the hunter doesn't realize, unless he knows some physics, that the light bent and the spear will go straight like this and go right through this point, the image of where the fish is. The fish appears here because of the idea, how I explained, that the brain sees light or thinks of light as traveling in a straight line. So the fish appears here. The arrow will go through that point and miss the fish. So if you're hunting fish with a spear, you have to aim slightly below where the fish appears to be. So in other words, if the fish is here and you're looking down at water, you want to aim, slightly lower like this so that it goes in and it looks like you're missing, right? But you're going to actually hit the fish. So you have to estimate that amount of refraction in order to get the fish. So water makes submerged objects appear at a shallower depth than they really are. Okay, so that's something that does actually show up on the Regents once in a while. Alright, so like I said, there's a little short video if you want to watch of this happening with a coin in a dish. But other than that, that's it for today, and I will see you in the next optics lesson.